Years. Today we can see some results regarding complex integration or complex analysis. The first result is if f(z) is analytic in a simply connected domain D and C is any closed curve inside D, then integral over C f(z) dz is equal to 0. So analytic and then any closed curve inside D, then we can say that integral over C f(z) dz is equal to 0. This is the named theorem, that is Cauchy's theorem. But the converse is not true. That is integral over C f(z) dz is equal to 0 inside the closed curve, but f(z) is not analytic. So converse of Cauchy's theorem is not true. Now we can see the second result. If 2 points z0 and z are any 2 points in R and gz is equal to integral z0 to z, that is 2 points f(z) dz, then you can say that gz is analytic. If this condition is satisfied, then we can say that gz is analytic and g dash of z is equal to f of z. Then the third one, this is the very important one, Cauchy's integral formula. If f(z) is analytic inside and on a closed curve, inside and on a closed curve, and A is any point inside C. So two conditions we need, that f(z) is analytic and the second one A is the point inside C. Then we can say that f of A is equal to 1 divided by 2 pi A integral f(z) divided by z minus A into dz. Cauchy's integral formula. Integral formula. Then the fourth one, the extension of the Cauchy's integral formula, that is nth derivative of f(z). Nth derivative of f(z) that z is equal to A is fn dash of A is equal to n factorial divided by 2 pi A integral over C f(z) divided by z minus A the whole power n plus 1 into dz. Now the fifth one, if gamma is a closed rectifiable curve in C, rectifiable curve in C, then A not in that region gamma. Okay, gamma is a closed rectifier and A is the point not in that gamma, then n of gamma comma A equal to 1 by 2 pi A integral over gamma dz divided by z minus A is called the index of gamma, or it is said to be the winding number of gamma around A. So this also we will see. It is n gamma comma A is called the index of gamma, or it is said to be the winding number of gamma around A with the condition that A not in gamma. Then the sixth property, en gamma comma A is equal to minus n of minus gamma comma A for every A not in gamma, because for the index number A not in gamma. Then the seventh one, if gamma is a closed rectifiable curve in C, then n gamma comma A is a constant for A not in C minus, that is that curve C minus gamma. So gamma is a closed curve in C, then n gamma comma A is a constant. So you can see the similarity between 7 and 8. Here if gamma from 0 comma 1 to C is a closed rectified curve and A is the point not in gamma, see the difference here, A not in gamma, then we can say that this is the formula of n gamma comma A. So n gamma comma A is an integer. Here n gamma comma A is a constant. Okay, A not in C minus gamma, here A not in gamma, n gamma comma A is an integer. Now the ninth one, Morera's theorem. If f(z) is continuous and for every simple closed curve in gamma together with the condition integral of C f(z) is equal to 0, then you can say that f(z) is analytic. So the condition f is continuous in a simple closed curve, integral over C f(z) is equal to 0, then you can say that f(z) is analytic. The same you can see that Cauchy's theorem. So Cauchy's theorem is f(z) is analytic in a simple closed curve, then you can say that integral over C f(z) is equal to 0. Here it is f continuous, that is as like the converse. f is continuous, then integral over c f z is equal to 0, then we can say f z is analytic. So this is Cauchy's theorem. That is the first result. Then ninth one, Liouville's theorem. If f z is analytic and bounded, then f z must be constant. So two conditions, analytic and bounded, then f z is constant. In short, we can say that a bounded entire function is constant. This is also the Liouville's theorem. Bounded entire. Entire means analytic in the whole plane. Analytic in the whole plane. Whole complex plane. That is analytic. Yes. So it is otherwise said as bounded entire function is constant. Then the 11th one, an analytic function with a constant argument is constant. So function you can take as f of z. So constant argument. So argument of f of z is equal to constant. Then you can say that the function is also the constant. That is given here. Analytic function with a constant argument is constant. The 12th result, same as the 11th one. If f z is analytic, so f z is analytic, then when we can say that f z is constant. So if one of the following condition hold, then we can say that f z is constant. So if real is constant, then you can say that f z is constant, or imaginary is constant, then you can say f z is constant, or modulus of the function is constant, then we can say that f z is constant, or f dash of z vanishes, f dash of z vanishes identically, then also we can say that f of z is constant. So for all these four property, the condition should be f z is analytic, then only this will be true. Now the 13th one, fundamental theorem of algebra. Every polynomial equation p of z, that is a0 plus a1 z plus a2 z square etc plus an z power n, with the degree is n greater than or equal to 1, and all the coefficients, that is an not equal to 0. If it's so, then we can say it has at least one root, or we can say that p of z is equal to 0 has exactly n roots, because here we can say that the degree is n. So we can say that it has exactly n roots, or you can say that it has at least one root. That is the fundamental theorem of algebra. Now the 14th one, f z is analytic inside and on a simple closed curve, and is not constant, analytic, and it is not constant inside C, then modulus f z assumes its maximum value only on C. If it's so, that is the theorem of maximum modulus theorem. This is the theorem of maximum modulus theorem. Similarly, minimum modulus theorem means everything is right, but in this place non-constant analytic, and also here non-zero inside C. Then f z assumes here it is minimum value. If it's so, then we can say that is minimum modulus theorem. Okay, for the minimum modulus, f z is non-constant. Here it is non-constant inside and on a symbol, and here non-zero inside. Modulus f z assumes its minimum value only on C, then that is minimum modulus theorem. Now the 15th one, if gamma is a rectifiable curve and f is a continuous function on gamma, then modulus integral gamma f z dz is less than or equal to integral gamma mod f of z into modulus dz, not dz alone, modulus dz. Then we need to know what is Cauchy's inequality. So for Cauchy's inequality, the f of z is analytic, then modulus f of z is less than or equal to m, then we can say that modulus f n dash of a is less than or equal to n factorial m divided by r power n. So Cauchy's inequality or Cauchy's estimate. Okay, thank you.